Welcome. We're so glad you're here with us for today's Harper Lecture. The Harper Lecture series began in 1979 with Hannah Holborn Gray speaking in San Francisco. As the need for critical thought remains apparent in all areas of life, we proudly continue this signature program to bring you stimulating conversations and fresh ideas. Our UChicago community is a global one, and we are thrilled that technology can help us stay connected to one another. As you enjoy today's lecture, please note the following items. Your camera and video will be off. However, we encourage you to ask questions. Please use the Q&A box at the bottom of your screen to ask a question at any time during the talk. Closed captions are available by clicking the box at the bottom of your screen. Click Show Subtitles to enable this feature. If you're having trouble with audio or video, please try shutting down programs in the background, or you can dial in from your phone. Thank you once more for joining us. We couldn't do this without you. Hello, everyone, and welcome to today's Harper Lecture, Beyond Our Sun, the Launch, Deployment, and Extrasolar Planet Science of the James Webb Telescope with Professor Jacob Bean. I'm Andrea Hodgman, Interim Director of Alumni Engagement and the Program Manager for the Harper Lecture Series. On behalf of everyone at the UChicago Alumni Office, thank you for joining us. Please allow me to introduce our moderator. Katie Bailey is the Director of Development for the Physical Sciences Division at the University of Chicago. Katie came to the university as an undergrad, earning her BA in Biological Science in 2010, and then continuing to earn a PhD in Human Genetics from the university in 2015. In addition to her responsibilities in science strategy and fundraising for the Physical Sciences Division, she has taught as an adjunct instructor in the college since 2017. Professor Bean and Katie, thank you so much for joining us. Katie, I'll hand things over to you.
Thank you, Andrea. I'd like to introduce Jacob L. Bean, who is a professor in the Department of Astronomy and Astrophysics here at the University of Chicago. Jacob's research focuses on the detection and characterization of planets orbiting stars beyond our solar system, so-called extrasolar planets or exoplanets. He joined the faculty of the University of Chicago in 2011 after postdoctoral positions in Germany and at Harvard. He received his PhD in astronomy from the University of Texas at Austin in 2007, and we've been so lucky to have him here at the university where he has generously shared his inspiring research with audiences as he does again today. Jacob, thank you, and the floor is yours.
Thank you, Katie. I'm really excited to be here giving this talk now because we're on the verge of a revolution in our understanding of the universe that only comes around once in a generation. And this revolution is enabled by the recent launch of a new space telescope known as the James Webb Space Telescope, or JWST for short. So I'm going to talk today about the launch of the telescope, the deployment of the telescope over the last several months, and the expected science in the area of extrasolar planets that we're going to be doing. So, the most perfect Christmas present that an astronomer could ever imagine came this past year. On December 25th, 2021, 7:20 in the morning Eastern Time, the James Webb Space Telescope, after decades of anticipation, was launched. And it was just an incredibly moving sight. It launched from French Guiana near the equator from the European spaceport on an Ariane 5 rocket. And I'm going to show a video here. The video is a couple of minutes long, and hopefully it's not too choppy for you. If it is, just bear with us. And I'm going to talk over the video while it shows some amazing pictures. So the James Webb Space Telescope is a collaboration between NASA, an agency we all know and love, but also the European Space Agency, ESA, and the Canadian Space Agency, the CSA. A few months before the launch in December, the telescope was delivered by ship to French Guiana and was then incorporated into a rocket that would launch it into space. And so these are just pictures of that installation on the top of the rocket into its mounting bracket and in preparation for launch. The James Webb Space Telescope had to be kept clean, so you can see that this integration happened in a clean room tent. That's the plastic walls surrounding the rocket integration. After a few days, it was moved to the launch pad. And again, like I said, Christmas morning, it had a successful launch into space. And it was just an extraordinary moment because after decades of design and development and construction, delays, concerns about cancellation, we reached this moment where we could launch the telescope. The launch was flawless. We got to see these beautiful images. And then just 30 minutes after launch, we had our last images of the James Webb Space Telescope as it drifted off into deep space. And the last thing that we got to see was the deployment of the solar panel to power the telescope for its next several years of operations. So that's the final view that we had of James Webb, drifting off into space. But the journey, as long as it had been to get there, was not over. And this journey was quite long. The James Webb Space Telescope was originally christened the Next Generation Space Telescope, and it was originally conceived in the 1980s. And this is a scan cover of a report that came out of a group of astronomers coming together at a place called the Space Telescope Science Institute in Baltimore, Maryland, to think about what would the next telescope be beyond the Hubble Space Telescope. And this is really an extraordinary report, an extraordinary vision, to see the future, because at this time, the Hubble Space Telescope had not even been launched successfully. It wasn't operational. But these people said, now that this is about to happen, what do we want to do next? And the telescope has gone through many iterations in its design. This was artists' conceptions of what the telescope could have looked like. They conceived of two different designs of the telescope, one a free-flying space telescope that you see there on the top, and another telescope that could have been mounted on the moon. The design that originally came to pass was a free-flying space telescope that eventually looked like this. And this is, again, an artist's rendering what the telescope looked like. The James Webb Space Telescope is a major advance for a couple of reasons. One is it's just large primary mirror. Telescopes are really quantified by their ability to spatially resolve astronomical sources and gather light from faint sources. So in that sense, James Webb is very powerful. Its telescope size far exceeds previous generations of space telescope, like the Hubble Space Telescope, which you've probably heard of, but also the Spitzer Space Telescope. The other advantage of James Webb is that it peers into the universe and detects infrared light. So the comparison here to the Spitzer Space Telescope is apt. That was a previous generation of infrared telescope. So the James Webb Space Telescope is really talked about as being the intellectual successor to the Hubble mission, but it's also the intellectual successor of the Spitzer mission. If you could imagine two people coming together and deciding to have a child, this is Hubble and Spitzer having the child of the James Webb Space Telescope, and then being shocked that for average sized parents, their child grows up to be 7.5 feet and plays in the NBA or something like that. So the James Webb Space Telescope is amazingly powerful because of its size and its ability to peer into the infrared universe. Like I said, though, the journey was not complete following the launch. There were months ahead of the project to deploy the telescope and for the telescope to reach its final station out in space near what's known as the Lagrange Point. So this cartoon picture illustrates what had to happen following launch. The launch was flawless, but then months of deployment and commissioning operations had to take place. And one of the key things that had to happen was the telescope first had to unfurl. The picture I showed here depicts what JWST looks like fully deployed and operational. But as you can see from the previous images in the video, it was launched looking like this. And the point was that James Webb had to fold up like so much origami to fit on top of a rocket inside a fairing that provided aerodynamic protection as the rocket launched into space. So the first thing that had to happen following the launch was a long sequence and multi-stage deployments, unfolding the sun shield, unfolding the primary mirror, deploying the secondary mirror, and a number of other numerous deployments. The sun shield bears special discussion. this is the protection of the telescope from the glare of our own sun. To peer out into the infrared universe, the telescope has to be kept extremely cold, and I'll quantify what that means in a minute. So the engineers who designed the telescope came up with this idea of a 5-layer sun shield. This sun shield is enormous. It's about the length of a tennis court. For this to be folded up and the telescope to be launched, the engineers had to design a way for it to unfurl and tension and do that very precisely. And so I just list here an extraordinary statement about how many things had to go right for this sun shield to deploy precisely. 178 total release mechanisms, 70 hinge assemblies, 8 deployment motors, 400 pulleys, 90 individual cables totaling roughly 1/4 of a mile in length. Astronomers were on the edge of their seats for months, waiting for this to happen, hoping it would happen, and nervously holding their breath. But it did. It unfolded brilliantly, and now the telescope is able to be kept at a very low temperature, allowing it to sense the infrared universe. On the hot side of the sun shield, which is constantly facing the sun, the temperatures can reach 260 degrees Fahrenheit. But because of the successive shielding of these different layers, the cold side of the sun shield that has the telescope and its sensitive instruments reaches temperatures of almost -400 degrees Fahrenheit, just a few tens of degrees above absolute zero. So we're an extraordinary piece of engineering. In addition to the sun shield, the primary mirror had to unfold. And like I said, the secondary mirror boom had to deploy. And that all happened successfully over the course of the first month following launch. Another thing that had to happen was JWST had to make its way to its station out in deep space near a place called the second Lagrange point, or L2. This position is about 1.5 million kilometers, or about 1 million miles from Earth, out beyond the orbit of the moon around the Earth, about 1/100th of the distance between the Earth and the sun. This Lagrange point, L2, is a very special place because at this place in space, the gravitational forces and the orbital momentum of the telescope orbiting the sun are balanced. And this being a UChicago lecture, I can't help but put in at least one formula to help you understand why a telescope farther away from the Earth than the sun farther away from the sun than the Earth is from the sun, orbits with the same orbital period around the sun. This is a consequence of an equation called Kepler's third law, which relates the orbital period of something orbiting a massive object, its orbital semi-major axis, that's A, the distance you are away, and the total mass that's interior to the object that's doing the orbiting. Because JWST is a little bit further away from the Earth and the sun combine to create gravitational force that holds the telescope in orbit around the common center of mass. If you add a little bit of mass to the sun's mass, that is, if you total and sum the mass of the sun and the mass of the Earth, then you get a correction factor that allows a telescope in space at this point to orbit with the same orbital period, but with a higher velocity, because it's traveling a greater length of distance in the same amount of time. So the schematic here on the left shows the different Lagrange points. There are actually 5 Lagrange points where the balance of orbital motion and the force due to gravity are equal. The L2 point is the one that the James Webb reaches, but there are other points where these arrows show the balance of the forces, orbital motion pulling you one way, gravitational forces pulling you other way. These are stable points out in space. So James Webb is far away from the Earth. It can keep its sun shield oriented facing the sun at all times and keep the telescope cold and the instrument stable. But it doesn't sit at the precise position of L2. It turns out from an orbital mechanics standpoint, it's more stable for the telescope to orbit the L2 point. And so it does an elliptical orbit around the L2 point. And this schematic is to scale, not really with the telescope, but with the Earth, the moon, and then the size of this orbit. James Webb, once it was launched from Earth into space, had to do 3 mid-course correction burns. And these were extremely delicate maneuvers because James Webb had to reach a precise velocity so that it inserted into this stable orbit around L2, but there was no way to counteract an over burn, let's say. If extra velocity had been imparted on the spacecraft, NASA would have had to abort the mission and let the telescope just fly off into space. And the reason is because once the telescope was deployed, it couldn't turn around. It couldn't turn its thrusters around to slow down. And so 3 precise burns reaching, stepping down to the right velocity were performed to insert it into this orbit. And that all went off really just perfectly. And that's a really important point. The James Webb Telescope was designed with a nominal mission lifetime of 5 years. And 5 years feels like just a short amount of time to an astronomer. There was hope that if the launch and these burns went well, the telescope would have enough fuel on board for 10 years of life. And that sounds a lot better from a scientific point of view. To make the most of this new facility, we need at least 10 years. But it turns out that the launch and these burns went so well that the James Webb Telescope should have 20 years of lifetime. That lifetime being limited by the fuel the telescope has on board for repointing and station keeping in this orbit. And so we're really excited that everything is working brilliantly with the telescope, and we're going to have this facility with us for the next few decades, barring any unforeseen problems. Okay, again, a very long road from launch. After the first month, when the telescope was being deployed and it was reaching its orbit at the L2 point, the instrument commissioning had to happen. James Webb has 4 different complex but powerful instruments, and they all had to be put through their paces to become operational. And the first thing that had to happen was the telescope mirrors needed to be aligned. You've seen images of the primary mirror of the telescope, 18 hexagonal segments, all mounted independently of each other. So the first light image, when JWST finally opened its shutters and peered out at the universe, it pointed at just a nearby star that was known to just be a single star sitting there in space, and took a picture. And this is what came out. And this is a terrible picture. 18 different images of the same star with all kinds of optical aberrations. But this is brilliant because this means that the light is hitting the primary mirror, it's hitting the secondary mirror, and it's going to the instruments. It's doing exactly what it needs to be doing. The only issue is that each hexagonal mirror is pointing in a slightly different place. And so the light is brought to a focus at slightly different positions in the focal plane of the instruments, and also in different focuses. So some are in and out of focus. So the first step was to identify which of these images corresponds to which hexagon. So they were able to do that, and it's a pretty simple process. There's actuators on the back of each hexagonal mirror, and you just pivot the image and take another picture and see which star in your picture moves, which dot of light moves. And so you can assign each of these images to each of the different hexagonal segments. Once you've done that, then you know where each segment is pointing, and you can align them. So the next step was just to make a picture of the hexagons themselves. So to arrange them into a pattern with fixed spacings between the images. And then finally, to bring those hexagonal segments into focus, because if you look at the previous image, some of these images are out of focus and some have other kinds of aberration. There's a lot of degrees of freedom of this hexagonal mirror, and so that needs to be tilted and brought forwards and backwards to bring these points of light and make them sharp. And now you have 18 individual sharp points of light that you know go with which hexagonal segment, and then you can bring them all to a common focus. And so that was done in late February of this year. And this is one of those images now where you have all 18 hexagonal segments working together. And at this point, you now have a 6.5 meter diameter telescope working as one single instrument. During this process, there's an instrument on board the telescope that allows you to take an image of what's called the pupil, which is just an image basically of what the telescope primary mirror looks like to one of the images, to one of the instruments. before the instrument, the mirror alignment process had taken place. This is what the image of the telescope looked like according to one of the instruments. You can see it's out of focus. One of the segments is more in focus than the others. But then afterwards, once the image alignment and mirror alignment process was done, they took another image and it looks like this. And this looks like just like a fake image, but this is an actual image of the telescope pupil, the telescope primary mirror, taken by one of the instruments. Now, people have asked the question, why aren't there any little cameras on the telescope to tell us whether this or that had deployed, or to see what the mirror is looking at? The reason is because since the telescope had to be folded up in so many different ways, you didn't want to add any additional complexity. Any additional cameras would require wiring that could get caught and snagged while the telescope could unfold. Also, any sort of cameras would be a source of heat that would corrupt the images of faint objects from outer space. And so it was decided that external cameras were not really needed. The only thing that you needed are sensors to measure positions of different components, and then the science instruments themselves, which are used to align the telescope and make sure that the optical path is free and clear. So this is an actual image of James Webb taken with one of the science instruments, all 18 segments working together, a hole in the middle because that's where the light hits the primary, goes to the secondary, and then goes back through the primary mirror, and the instruments are behind the primary mirror of the telescope. And then you've got the 3 struts holding the secondary mirror out away from the primary mirror. And so finally, the real first light image of the telescope is shown here, where you've got now as sharp an image as the telescope can make of one of these stars. And now you're seeing also images, the background behind the star. And what you see here is a preview, just a taste, I think, of what James Webb is going to reveal about the really distant universe. That is, if you point anywhere in space and look, it's galaxies as far as the eye can see. And so all of those points of light are distant galaxies. And some of them may be incredibly distant. That's something that NASA hasn't told anyone yet. What are the distant galaxies that just happen to be present in this image? But it's an extraordinarily rich image, and it's just a commissioning image. It's just an image taken to make sure the telescope can bring the light from distant sources to a point and deliver that light to the instruments. Following the mirror alignment, the next thing to do was to turn on all the different instruments. It was the NIRCam instrument, which is shown here in the center of the diagram, that was used to perform the mirror alignment. But there are other instruments, the NIRISS instrument, the MIRI instrument, NIRSPEC instrument, the fine guidance sensor as well. These are 4 science instruments: NIRSPEC, NIRCam, NIRISS, and MIRI, and then the fine guidance sensor, which is not used for science, but is used just to maintain the pointing of the telescope during exposures where you're doing science. So NIRCam was used to align the telescope mirrors, and then the other instruments were turned on successively. And it's quite interesting because they all share what's called a focal plane in the telescope. The light comes to a focus, and it has a physical size corresponding to different parts of the sky, different parts of the field of view projected onto that focal plane. And so the instruments and their detectors share a focal plane. So this is a reconstruction of a single pointing of the telescope and all the instruments taking data at once. And there's zoom in details on these. These are very detailed images that this picture here doesn't even really do justice to. There are thousands of pixels along each axis of each one of these squares. Just want to highlight one of the images in particular, comparing the power of JWST to the telescopes that came before. This is an infrared picture taken previously with the Spitzer Space Telescope, so something that's 85 centimeters in diameter, at a similar wavelength as the alignment image taken here with the MIRI instrument on James Webb, a telescope that's about 8 times the diameter, so should deliver images that are at least 8 times better. And you can see here just the dramatic improvement. You've increased the spatial resolution, and so you can see finer details. You also increase the sensitivity, which helps with the dynamic range, and again, also draws out more details from the image. This is infrared light, and so you even see wisps of diffuse gas that exist in this galaxy. This is a picture of one of the Magellanic Clouds, which is visible to the naked eye in the southern hemisphere sky. And you can see hot but diffuse gas radiating in the infrared. This is a region of star formation, and this is one of the science themes of what JWST will explore. How do stars and their planetary systems form and evolve? And so JWST will study diffuse gas and nebula and disks and young stars that are embedded in those regions. And you can see that the detail is just going to be extraordinary. JWST has to be very cold, though, to see its infrared light. Like I said, roughly minus 400 degrees Fahrenheit. At this temperature scale, the Fahrenheit unit doesn't make a lot of sense. And so scientists use a unit called kelvins, which measures the temperature above what's known as absolute zero. It measures the actual, there's a direct correlation between temperature in kelvins and the actual kinetic energy of particles in the gas or in a solid. At absolute zero, all motion ceases, and that's a condition that has been created in a physics laboratory. Here, we're a few tens of Kelvin above absolute zero for the majority of the telescope and the instruments. With one exception, the MIRI instrument, which is designed to look at the longest wavelengths that JWST has access to, is held to a few temperatures of just a few Kelvin above absolute zero, about 4 Kelvin, so just a few degrees above absolute zero. So JWST is now quite cold. It deployed its sun shield, and for the last 5 months, the instruments have been sucking heat out of the telescope and radiating it off into space. The radiator sits on the hot side, and it's basically just something that's painted black to radiate energy away. And once that energy is pulled out of the cold side of the telescope, there's really not much that can heat the telescope up. The cold temperature of the vacuum of space is 3 Kelvin. So you can't get, it's harder to get lower temperatures than that. But the operation temperature here is just a few tens of degrees above Kelvin. Really extraordinary engineering achievement. Like I said, the temperatures had to drop. The temperature started upon launch at roughly room temperature, actually a little bit warmer. French Guiana it was launched from basically a rainforest near the equator. So temperatures upwards of 300 Kelvin to now temperatures of below 50 Kelvin. Just a comparison, 300 Kelvin is considered about room temperature. That's about 75 degrees Fahrenheit. And so you can see on these plots different temperature measurements for different parts of the spacecraft. The hot side has remained at roughly 300 Kelvin throughout, but the cold side, after radiating that energy to space, has cooled off dramatically. And especially the MIRI instrument, which is given by this light blue line here, has been successively cooled to just a few degrees above absolute zero. There's an internet site that NASA runs where you can actually view JWST's orbit out in space, and it's really fun to watch that. And you can scroll around and move things around and see how JWST's position compares to where the moon is orbiting the Earth and the whole system relative to the sun and the other planets of our solar system. You can see here also some asteroids as well, and some of NASA's other space telescopes, Chandra, an X-ray telescope. TESS is a small transiting planet finding mission using small telescopes. And so I invite you to just explore the web, because NASA has put a really amazing amount of material out there that allows you to follow along with the success of the James Webb mission. So now I'm going to talk a little bit for basically the next 10 to 15 minutes about the extrasolar planet science that JWST is going to do. This is the thing that I work on. This is the topic that I work on. And I've been waiting for James Webb for about 15 years of my research career. I study planets that orbit other stars, so extrasolar planets, or exoplanets for short. There are more than 5,000 planets known around other stars. The first ones were found in the mid-90s, and as technology and observing techniques have improved, what we have found is that planets exist around almost every kind of star and come in a wide diversity of properties. This plot here is just a one-plot snapshot of what extrasolar planet science looks like right now. If we look at planet mass in Jupiter units on the y-axis and orbital semi-major axis, distance from the host star on the x-axis. This is a what's called log-log plot. So every major tick mark is another factor of 10 here. And the reason you need to use this kind of scaling for the plot is because planets come in a wide range of sizes. We see that in our own solar system. We have Earth at 1 Earth mass. Jupiter is 300 times the mass of the Earth, so already 2 orders of magnitude there. Planets around other stars are even wider variety of diversity. They orbit their stars at a wide range of distances as well. We found them with an extraordinary range of different techniques, and these different techniques tell us different things about the properties of the planets. There are parts of this diagram that don't have points, and you may be wondering, do planets exist in this part of the diagram, or do they not? Probably they do, but we don't know. So really anywhere where you see, especially in the bottom right corner of the plot, just wide open white space in the plot, that just means our observing techniques and our technology are not sensitive enough to find planets in that regime. Everywhere we've looked for planets, we've basically found them, and we found them in more numbers and with a wider range of properties than we expected. Now, this plot, though, makes the planets seem like anonymous astronomical objects, whereas instead, these are worlds. These are worlds, each one is interesting as all the objects of our solar system, thousands of them around other stars. The thing that I'm most interested in exoplanet science is to understand the detailed properties of these objects. So to go beyond just what are their masses and how far from their stars do they orbit, I want to understand their detailed properties. What are their atmospheres made out of? If any of them have surfaces, what's the surface conditions like? What are the interior structures of these planets? This requires more work than just finding the planets. This requires characterizing the planets, often with multiple techniques, working together to build up a picture, a detailed picture of the planet, measure their mass, their radius to determine their density, infer what they're made out of, probe the atmosphere using spectroscopy. Probing the atmosphere with spectroscopy is really my specialty and the thing that James Webb will excel in doing for extrasolar planets. The kinds of questions that we like to answer, I like to frame them as, what are these planets like and where did they come from? What are these planets like? Well, if we look at all the objects of our solar system that have atmospheres, the atmospheres display a wide range of physics and chemistry. Planets around other stars give us access to planetary atmospheres as a laboratory for physics and chemistry beyond what we see in the solar system. You have giant planets that are not cold like Jupiter and Saturn, but instead are superheated because they're close to their host stars. You have planets with atmospheres that don't even have an analog to things that we see in the solar system. So this allows us really to understand the character of planets. It also turns out that atmospheres are diagnostic of how planetary systems, planets themselves form and evolve. Jupiter, for example, its atmosphere was pulled in from the protoplanetary disk that the planet formed out of. Thus, its composition is a fossil record of the conditions in the disk that led to the planet's formation. Rocky planets like the Earth have what's known as secondary atmospheres formed by volcanic outgassing. And so there, the composition of the atmosphere tells you about the internal geology of the planet. So what are they like? Where do they come from? It all hinges on taking spectra of these objects to reveal their atmospheres. I focus on planets that do what's called transit their host star. That is, they have a fortuitous orbital alignment such that they pass between their host star and our line of sight once per orbital period. These planets that transit actually give us a number of ways to access the atmosphere. When the planet passes in front of the star, some of the starlight filters through the planet's atmosphere. And if you do a difference measurement between in and out of transit, you can subtract off the influence of the star and you're left with the planet's spectrum. Planet's spectrum is known as a transmission spectrum in this case. But we have other probes as well. Turns out the planets are emitting and reflecting light. And you can see that, you can distinguish that from the light of the host star by seeing when the planet goes behind the star, the light from the planet gets blocked. Again, a difference in and out of this eclipse tells you what the spectrum of the planet is. Also, for some planets, we can watch them orbit the star, and they rotate on their axis as they orbit, and we can see their day sides and night sides come into view. For all these measurements, it's a combined light technique that involves resolving the planets from their stars using temporal techniques rather than spatial. We don't look up at the star and the planet and see when this happens. All we do is see the total amount of light, and how it changes over time allows us to get the spectrum of the planet. Once we have the spectrum of the planet, then we can deduce the composition of the atmosphere. Over the last 10 years or so, my research group has made a lot of use of the previous key space telescope, the Hubble Space Telescope. We used an instrument called the Wide Field Camera 3 that was installed in the final servicing mission that astronauts undertook to improve the Hubble's capabilities. We've been using this instrument to take spectra that map planets as three-dimensional objects. And I got just a little simple movie here that we made from a paper a few years ago, where we measured the thermal emission of the planet, the infrared light the planet was emitting as it rotated on its axis. Now, what was really happening was the planet's orbiting its star, but it's synchronously rotating with its orbit, meaning that it rotates once on its axis, once per revolution around the star. It's an analogous situation to what the moon does around the Earth. The moon is synchronously rotating around the Earth. And so when we look up at the night sky and see the moon, we're always seeing the same face of the moon. Now, an external observer observing the Earth-Moon system would watch the moon go around the Earth and would watch the moon actually rotate during that orbit. Same thing here. Planet's going around the star, and we just watch it rotate as it orbits. So one orbital period is one rotation period. We take spectra as a function of time. We subtract off the contribution from the star, and we're left with this. And what we have here is a spectral signature of water absorption in the planet's atmosphere. This is hot water vapor in the planet's atmosphere, and we're able to map the abundance of the water as a function of longitude on the planet, and use this diagnostic as well to tell what the temperature structure of the atmosphere is, how the temperature, and that's the top right plot, how the temperature changes with altitude, in this case pressure, that's a proxy for altitude in the atmosphere. So you can see this planet, which has a permanent day and a permanent night side. It's hot on the day side, and it's emitting a lot of light, and it's much colder on the night side. And we can map the water abundance throughout the planet. So this tells us about the physics and the chemistry of the atmosphere. And also, when we measure this water abundance, we use that to understand how this planet formed. So this is what we were able to do with Hubble. And it looks cool, and I was really excited to do it. But this is really just a small snapshot of the planet's whole spectrum. And indeed, our uncertainties on these data are not sufficient to say really a lot of detailed information about this planet. James Webb is going to blow this area open because it has a larger mirror, thus greater sensitivity. It has broader spectral coverage, so we get more information. Whereas before, when we took these data, and it took a ton of effort to get that result, we only had one absorption band due to water. And that was great, but we would have loved to see multiple absorption bands due to water. That would allow us to measure the abundance more precisely and then constrain the temperature structure of the planet's atmosphere more precisely. On top of that, we want to see the full range of chemical species that exist, but we just couldn't due to our limited spectral coverage. With James Webb, we should be able to get data like this in a single snapshot and then do the same kind of experiment where we watch the planet orbit and take this spectrum once every hour or so during the planet's orbit and build up that kind of movie, but now in much more exquisite detail, seeing it at higher precision, seeing multiple bands of different chemical species, and then really understanding in more detail what the composition and temperature structure of the atmosphere is. And we'll be able to do this, I think, just so easily with James Webb, so easily that the planets that were the hardest ones to do and that we could barely do before with Hubble, we will do them so easily, and then we'll be able to do even more difficult objects. And so that really leads to the final part here, which is that we've been studying gas giant type planets like the data I showed you before, and that's really exciting for understanding how those kinds of planets form and evolve. But another motivation for studying the atmospheres of other worlds is to ultimately look at the atmospheres of rocky planets that may be like our Earth and to understand whether those planets are habitable or not. Do they have liquid water? Do they have the right temperature and pressure for liquid water to exist on the surface? Are there signatures of life, biosignature gases in the atmospheres of the planets? And can we detect those? And can we infer the existence of life? And so that's really the frontier that JWST will open. And we're really excited to be doing that. One of the first things that we're going to do, though, when we finally have the capability with JWST to look at the atmospheres of rocky planets, is we want to see if the rocky planets that are being discovered around other stars, the terrestrial planets, actually have atmospheres or not, because we're not sure if they will. If you look at the rocky planets of our own solar system, half of them have atmospheres, half of them don't. Earth and Venus have significant atmospheres of different thicknesses. Mercury and Mars don't. And so we'd like to understand what causes rocky planets to form and retain an atmosphere in the face of processes that could, that a rocky planet could lose an atmosphere or never form one to begin with. And so a few years ago, in anticipation of JWST, my collaborators and I came with we think, a fairly clever way to do this. And that's just to take a snapshot of the planet and to measure its total emission. How much total light in the infrared do we get from the planet? And it turns out that the atmosphere, the presence or absence of an atmosphere, and the presence and the certain thickness of the atmosphere has a telltale impact on how much energy the planet emits. And the reason is these planets that we're studying, they have permanent day and permanent night sides. And so the question of how much energy makes it to the night side is a question of energy transport. If there's no atmosphere, there's no energy transport. And so the day side will be hot, the night side will be cold. As you add an atmosphere, make it thicker and thicker, the atmosphere will serve to moderate the temperature differences because it transports heat from day to night. Thicker atmosphere, actually colder night side, and smaller contrast between day and night. So that's what's being shown here on the left is if you observe a whole planet during an orbit and you see this phase curve, we call it, it looks like a sine curve of different heights. The height will be extreme if there's no atmosphere. That means there's a large contrast between day and night. It will be shallow if there's a thick atmosphere transporting heat. And we've quantified how the energy transport will depend on the thickness of the atmosphere. Whether you have an atmosphere that's a tenth the mass of Earth's or equal to Earth's or 10 times the mass of the Earth, that will impact the heat transport and will impact this temperature difference between day and night. So what we're actually going to do is just focus on measurements when the planets go behind the star at secondary eclipse, and we're just going to take the temperature of the day side. And that will very quickly tell us whether these planets have atmospheres or not through the impact of the heat transport. So we're going to be able to do this for a bunch of rocky planets just in the first year of JWST operations to tell which ones have the atmospheres, which planets deserve further scrutiny with detailed observations to reveal the composition and real thickness of the atmosphere. So that's one of the things that we're going to be doing with James Webb. We're doing this actually for planets that are being discovered with another experiment that I'm actually involved in. A few years ago, my team built a new planet detection instrument called Maroon X, which we installed on the summit on a telescope on the summit of Mauna Kea in Hawaii, the Gemini telescope, an 8-meter telescope shown there on the top left. Here are just some pictures of the instrument on the bottom right. It's a very stable instrument because we measure the wobble of stars to see unseen planets, to detect unseen planets. So it sits inside a vacuum tank that's inside a controlled temperature chamber that again sits deep inside the telescope support structure. And we control the temperature of the instrument and the pressure inside the instrument to very precise values. Maroon X has been operational for a few years, and we've started to find planets. We found the planets that JWST is pointing at in its first year of operations. And so it's really an integrated research program where we find planets using so-called radial velocity measurements. And I know this is a somewhat technical diagram, just to show that Maroon X can find terrestrial planets orbiting other stars very easily and can measure their properties very easily. This system is a very nearby system containing a rocky planet. It stands out because it's quite nearby, which is great for James Webb to allow us to get the most sensitive measurements of seeing whether it has an atmosphere or not. And if it does, what are the properties of those atmospheres? It's a planet, we think, that has an interior structure almost identical to that of the Earth. If you look at this green line in this radius mass diagram, The planet that we have here sits right on that line. And so it's a nearby rocky planet that's orbiting a nearby star. Its interior structure is like the Earth. And in just a few months, we're going to point James Webb at it, and we're going to say, this planet has an atmosphere or not. And so we're really excited about this. We're doing this for many rocky planets that are being discovered with Maroon X and that we're targeting with James Webb. Today is a pretty cool day because we found out from NASA finally when the science data are going to start to release, and that's going to be on July 12th of this year. So in about 6 weeks or so, we're going to start getting first science data from James Webb. The commissioning is nearly complete. The final touches are being put, and it's about to be open for business. I keep this spreadsheet handy, which just keeps track of the different exoplanets and observations that my own team is involved in. You can see here our first observations that we're going to get are on July 10th. Those data won't be released until after this release of first science data on July 12th, but we're ready to go from the very beginning. And you can see in these dates that the fire hose of data just turns on. 4 days later, 4 days later, 4 days later, 2 days later, 4 days later, just a few days after that. And it's just going to keep going. And this is just the first year of observations. And it's going to be an extraordinary fire hose of data. And we're gearing up to analyze those data. And in just a few months, we're going to have answers about extrasolar planets that we have pondered for more than a decade now. And it's going to be really exciting. I don't want to mention, I've just got 2 more slides here, so bear with me. I don't want to skip over mentioning the Giant Magellan Telescope project. In the interest of time, I can't say too much about it, but some of you may know that the University of Chicago is involved in building this new giant telescope on the ground in Chile, in the Atacama Desert of Chile. The James Webb Space Telescope, just in one sentence, fits into this science very well. It's going to allow us, for the rocky planets that we find to have atmospheres and that we find with James Webb could be conducive to life, the Giant Magellan Telescope will allow us to look at those planets and see if life actually exists through the detection of biosignature gases. I don't want to belabor this point because this talk is really about James Webb. And so I just want to finish by trying to answer a question that's already been posed in the registration. And the question is, why are we doing this? We have so many problems here on the Earth. Let's be honest. There's war. There's a pandemic that's still going on. There's poverty. There's hunger. There's social inequality. There are people, children not being educated. There are children being killed by crazy people. We have so many problems here on the Earth. Shouldn't we just focus on solving those problems? And so I have a lot of answers. There are a lot of answers to this. You can make answers to like, well, this inspires people to get an education. It improves our workforce. It provides for national defense because it increases our science and technology capabilities. I favor personally a different kind of answer than that. Certainly there are practical uses for what we're doing. This is basic research and it flows into society in many different ways. But I like to take a step back and think about sort of the sociological implications of what it is that we're doing. And this kind of argument for why to do big science projects was really outlined first by a person named Dr. Wilson, who is the first director of the Fermi National Laboratory. And in a 1969 congressional hearing, he was grilled by senators about why we should be doing a new accelerator project at that time. And his answer boiled down to, no, it has no practical use. It will not improve our chances of winning the Cold War. It will not provide for the national defense. Why do we do it? And you can just, read it quickly here. His point is, we do this because these are things that humans must do, that they value, that it is about relationships between people. It makes our country a place worth living in, a place worth defending. Otherwise, what are we doing? And I like to think of this as really the best answer for why we're doing this, is because it makes us who we are and it makes us a more unified people. When I was asked by the Chicago Tribune to comment on the launch of James Webb back in December, I thought about this mirror that we've put into space. And I'm like, well, what do you do with mirrors? Well, the astronomer answer is use it to point into outer space and gather a lot of light. But we also use mirrors to look back at ourselves. And during the Christmas season, the holiday season, is a moment for this kind of reflection. And I thought, what this mirror is going to do is, if we look up at it, we're going to see the best of ourselves doing this science. It's aspirational. It's from curiosity. It was done in a multinational collaboration of thousands of people working together for one goal. And I found this artwork actually as I was preparing these slides that kind of just illustrates that this telescope is not just reflecting the cosmos back to us, but ourselves back at ourselves, that we can see each other more clearly. And so that's really my answer to why we're doing this, is that it makes us human and it makes us a unified people. So with that, that's the end of the lecture, and I would welcome Katie to come back and moderate question and answer session. Thanks for your attention.
And thank you, Jacob, for that fascinating presentation on the launch of JWST, the possibilities for exoplanet characterization, and for the philosophical perspective there at the end. It really put it all into a greater context. Starting back with, what is JWST going to observe? Is there a prioritization order for specific targets? Do you have to submit requests for what JWST is going to look at? And
that's a great question. Yeah, so JWST is an open access facility that anyone in the world could propose to use for their science. And so there's a rigorous proposal and review process that happened. And there were many different proposal and review processes that happened over the last few years. And so there's different kinds of programs that JWST will do. JWST will point at one of everything in astronomy in its first year, from the most distant galaxies that are known to more nearby galaxies that are dominated by dark matter, and we want to understand what dark matter is, to planets orbiting the nearest stars, which I'm fascinated in. So it's actually a competitive peer review process that's driven primarily by the community's interest and what science that they want to do. This isn't a top-down thing where NASA is saying, you have to look at this, that, and the other thing. It is really driven by the entire astronomical community through proposals, through peer review, and it's put together that way. Once this is done on a yearly basis, so the observations for the first year are now planned, and they're prioritized mainly by what is efficient use of the telescope. Since the telescope is so large, for it to move and point at different parts of the sky, it takes a lot of energy. And it also changes the temperature of the telescope, which they want to minimize how that does. So once the first year of observations have approved, then the people that run the telescope schedule them efficiently. And then it just so happens where your object in the sky is, whether you have some sort of time constraint, where the telescope can point. And so once science operations begin, basically in July, and we start getting data just July 12th, it's just going to be a series of just whatever gets scheduled and done from those first year of observations. And so I'm really lucky to be involved in about 300 hours of science programs for extrasolar planets. And you can see that list. It's just going to they're going to do that, they're going to do that, they're going to do that, and the data are just going to pour in. And each data set is going to be extraordinary.
Thank you. You also spoke a bit about the strengths of JWST over the Hubble telescope. Does the Hubble telescope now just come out of commission, or does that keep collecting data? And you also spoke a bit about the GMT at the end. How does JWST dovetail with GMT? What are the biosignatures that might be looking for?
Right. So Hubble still has advantages over JWST. Hubble was a ultraviolet optical short wavelength infrared telescope. And so while JWST supersedes Hubble in the sort of long wavelength optical and infrared, it has no capabilities for UV observations, ultraviolet observations. And so that's an area that Hubble will continue to excel in throughout the remainder of its life, which could be another 8 years or so. And so there's an increasing focus on ultraviolet observations. Also, sometimes Hubble can take some first observations of something to see whether it's worth spending JWST time on. And so there's a great synergy there. Your other question was about the connection between GMT and JWST. So the main quality of a telescope is really how large its primary mirror is. JWST is 6.5 meters in diameter. That's comparable to the largest ground-based telescopes that we have right now. But from the ground, you can build even bigger telescopes much more easily, faster and cheaper. And so the giant Magellan telescope's primary mirror is going to have an effective diameter of 25 meters, so 4 times that of JWST. And so what that will allow you to do is, in the wavelengths of light that are accessible for ground-based telescopes, you will be able to achieve better spatial resolution and higher sensitivity. Now, JWST will access wavelengths that GMT cannot observe. The influence of Earth's atmosphere will prevent that. But one of the advantages of having such a large telescope that has such sensitivity is that you can increase your spectral resolution. Spectral resolution is your ability to detect the subtle signatures of different gases. And so in the case of biosignature gases, the prime biosignature gas on the Earth is oxygen, molecular oxygen O2 and ozone O3. These are 2 molecules that exist in Earth's atmosphere that would not be present if life didn't exist. They're highly reactive gases, and if they weren't constantly replenished, they would be drawn out of the atmosphere by reactions with Earth's surface, the rocks. That we would oxidize the rocks, and the surface of Earth would look like Mars. It would be red instead of blue and green. And so seeing the signature of oxygen in other planets is a potential way to identify life, but it requires very high spectral resolution. That's not something that JWST can do. Its instruments perform spectroscopy, but at lower resolution. So you can see things like water and carbon monoxide and carbon dioxide and ammonia, but you cannot see the more subtle signatures of oxygen. That requires higher spectral resolution. That this then requires a larger telescope, because you have to feed a different kind of instrument, a high resolution spectrograph that then spreads the light out so much that you need a lot more light to get your signal to noise, your detection capability for oxygen. So that's sort of a long-winded answer, but telescopes on the ground and telescopes for space are essential for astronomy, and they do different things. And especially for extrasolar planet science, we have them working together in a unified way to answer, to drive towards the answers to the questions that I outlined.
That's great. Thank you. What's the most exciting thing you could imagine coming from the James Webb Space Telescope? And similarly, the most surprising discovery?
The thing that I want to know the most is, like I said in the talk, I want to know if rocky planets around other stars form and retain atmospheres like Earth did, like Venus did. And I want to be able to tell how thick are those atmospheres. What kinds of planets generate atmospheres that are too thick, like Venus, or just right, like Earth? And then do those atmospheres have those biogenic molecules that we want to see, the water and things like that, the things that we know are essential for life? So I want to find the planets that will point the GMT at, and then we'll look for signatures of life. What am I going to be surprised by? That's the point of a surprise, is I have no idea. But I can tell you, starting in 6 weeks, every week it's probably going to be like, astronomers discovered this amazing thing and this amazing thing. Because like I said at the very beginning, it's going to be a transformational advance that is something that only happens in astronomy like once every generation. If you're old enough to remember those first images from Hubble and how that opened our view to the universe, this will be like that again. And I think it's going to be a wonderful time. I've been working my whole career for this. I feel like this is going to be the highlight of my career. In all areas of astronomy, there are going to be breakthroughs. And I just can't wait to see it all. I think it's just going to be amazing.
Does that include breakthroughs around dark energy and dark matter? Absolutely.
I think in the area of cosmology and the fundamental physics of the universe, there are going to be big breakthroughs. For example, studying galaxies that are mostly dominated by dark matter. That's something that's been quite hard with existing telescopes. And we have people on our faculty here in Chicago who are studying those kinds of galaxies and will reveal more details there. We also have people who are studying the evolution of the universe. For example, measuring this thing known as Hubble's constant, which has described how the universe has expanded and enlarged to become the place that it is right now. There's actually quite a lot of tension in measurements of the Hubble constant from different probes of cosmology. And that can be indicative of new physics that we didn't anticipate. JWST will help us measure the Hubble constant in multiple different ways to determine if that's a real discrepancy between what techniques give what value and whether that represents some sort of evolutionary history over cosmic time. And then that will give us a hint perhaps of what the new physics could be that we're missing. In astronomy, we know that we're missing tons of physics. We have this stuff called dark matter. We have this stuff called dark energy, and they make up the majority of the universe, even though they don't emit light. And we're not made of them, right? And stars and planets aren't made of them, yet they're the majority constituents of the universe. So we already know there's things that we're missing, just fundamental pieces of the universe that we're missing. We'll get further insights to what those things are, and then we could, just open up discoveries of other things that we're missing.
As a final question, perhaps premature, but what's next? These telescope projects take a really long time and a lot of money. So how do we start planning for the future?
What a wonderful question. So very much like my predecessors had the vision to anticipate designing James Webb before Hubble even launched, I've tried to carry that forward by having a similar vision of before James Webb launches, we need to already be thinking about the next telescope. And so for quite a while now, astronomers have been doing that, pursuing that, and coming up with ideas. And I've played a role in that over the last 10 years. And so we recently had what's known as a Decadal Survey in astronomy and astrophysics in the United States. That's where the entire US astronomy community comes together and tries to prioritize what are the big goals for the future. And so out of this process of designing what's come next, the recent Decadal Survey report, which came out last fall, prioritized a new telescope, new space telescope beyond James Webb. It would be roughly the same size as Webb, but it would have operate at shorter wavelengths, more comparable to Hubble. And then it would have advanced instruments that will allow us not to see planets using these time techniques that I've been using, but to then spatially resolve them from their host stars and to see these pale blue points of light orbiting other stars that are representative of potential Earth-like planets. And so that's the future. And that's probably going to happen in the 2040s. So it's more than 20 years away. So between now, with JWST coming online, 10 years from now, the Giant Magellan Telescope, and then another 10 years after that, the launch of this new, what we call direct imaging space telescope, astronomy has set out a path to furthering our understanding of course, everything in the universe, but specifically planets around other stars and that search for life on other planets.
Thank you again, Jacob. And with that, I'd like to welcome Andrea back for some closing remarks.
Oh yeah, thank you so much, Professor Bean, for sharing your work with us. This is so exciting. And thank you, Katie, so much for being here to extend the conversation with the audience. And thank you again. We'll see you soon.